Dear students, you are going to learn mutarotation of glucose now. First, I will explain what is meant by mutarotation. Mutarotation is the spontaneous change in the specific rotation of an optically active compound in solution with time to an equilibrium value due to the change in the equilibrium between two anomers when the corresponding stereocenters interconvert when dissolved in water. In general, cyclic sugars show mutarotation as alpha and beta anomeric forms interconvert. Example, glucose and fructose, they are monosaccharides. Maltose, which is a disaccharide, and among the disaccharides, sucrose does not show mutarotation. Now first we will see what are anomers and what is meant by specific rotation. Anomers. Anomers are epimers that differ from each other in the configuration of C1, that is carbon 1, if they are aldoses, and in the configuration of C2 if they are ketoses. In general, epimers are diastereomers. They are differing at configuration at any one of the carbon atom. But anomers are special case of epimers in which the configuration changes at the first carbon atom in the case of aldoses and second carbon atom in the case of ketoses. Now we will see specific rotation. It is defined as the degree to which a sample of known concentration of an optically active compound may rotate the plane polarized light when placed in a 1 decimeter sample tube is referred to as specific rotation. And the formula used for finding out the specific rotation is alpha D capital T, okay, as a subscript capital D and a superscript capital T, that refers to temperature, is equal to alpha observed divided by C into L, where alpha observed is the observed angle of rotation, how much angle of rotation takes place for the plane polarized light. If the rotation is in the clockwise direction, then that substances are said to be textro-rotatory substances. If the optical rotation is changed in the anti-clockwise direction, left, means they are said to be levo-rotatory substances. Then alpha, the specific rotation, is measured in degrees and observed angle of rotation is measured in degrees. C is the concentration in gram per ml and L is the path length. The unit is decimeter. Using this formula, we can calculate the specific rotation. Glucose exists in two anomeric forms, alpha anomeric form and beta anomeric form. The alpha anomeric form of glucose has got the optical rotation value is plus 112 degree and the beta anomer has got plus 18.7 degree. And for mutarotation of glucose is defined as the change in the specific rotation representing the interconversion of alpha and beta forms of D-glucose to an equilibrium mixture. That is, when alpha D-glucose is dissolved in water, the specific rotation value is decreasing from 112 degree to the equilibrium value plus 52.7. Afterwards, this value does not change. Similarly, when beta D glucose is dissolved in water, the specific rotation value plus 18.7 starts increasing with the time till it reaches the equilibrium value plus 52.7 degree. When a crystalline sample of either anomer, it may be an alpha anomer or beta anomer, alpha glucose or beta glucose, is dissolved in water, the specific rotation changes over time until 52.7 degrees reached. That is explained in the following image. Say, for example, at the bottom, we are having the specific rotation value, okay, 18.7. It is the beta anomer. As the time increases, we see the value in specific rotation value increases till it reaches 52.7. Afterwards, it won't increase. Similarly, if we start with the alpha D glucose, what happens now? This anomer has got a specific rotation value 112. Therefore, as the time increases, it starts decreasing till it reaches the equilibrium value 52.7. Afterwards, it won't decrease. This change in the specific rotation is explained in the following image. If we take alpha D glucose and beta D glucose in solution, what happens now? They can, alpha and beta configurations can change spontaneously through intermediate open chain formation through the process of mutarotation. And there is only a small amount of open chain glucose is present. This we can explain using the following structure. The Fischer structure, so open chain structure, in the middle we are having a open chain structure. So trace amount is present. For this, the optical rotation value is 52.7. If we start with beta D glucose, beta form of the glucose, whose optical rotation value is 18.7, what happens now? When dissolved in water, it starts converting to equilibrium structure and it starts converted to alpha form. The optical rotation value increases from 18.7 to 52.7 till it is converted to open chain structure. Similarly, when we take alpha D glucose with this specific rotation value 112, when water is added, it is converted to open chain structure and that is converted to the beta form. Okay, because of these interconversions, there will be a change in the specific rotation. The equilibrium specific rotation value is 52.7. The alpha and beta glucose, the first carbon atom, if hydrogen is present in the left hand side and hydroxyl group is present on the right hand side, then that form is said to be alpha form of glucose. And in the beta form of glucose, the first carbon atom, hydroxyl group is present in the left hand side and hydrogen group is present on the right hand side. In the open chain structure, the first carbon atom we are having a CHO aldehyde group, and that first carbon, during the cyclic structure formation, that first carbon atom is connected to fifth carbon atom via the oxygen. The first carbon atom is said to be anomeric carbon atom. Depending upon the configuration, how the hydrogen atoms and hydroxyl groups are attached to that anomeric carbon atom, we can classify them as alpha and beta form. Below that, here it is the Haworth structure, cyclic structure, pyranose structure. Pyranose is a 6-membered form, ring structure, having oxygen at one of the corner. In the beta form, the first carbon atom, hydroxyl group is at the top, above the ring, and hydrogen is at the bottom. In the alpha form, the ring, hydrogen atom is at the top and hydroxyl group is at the bottom. In the middle, we are having a open chain structure where the fifth carbon atom hydroxyl group, the first carbon atom mono, the fifth carbon atom is connected to first carbon atom via the hydroxyl group of oxygen, so that we can get this Haworth structure. Hope you might have understood the process of mutarotation and definition for mutarotation and how we are getting change in the specific rotation value for glucose. Thank you.